to set the scene, we have $500,000 in the bank. We have just moved into an office. We have no cell lines, we have no lab, we have no software, and we've promised to build a brain-computer hybrid. What could go wrong? The answer is quite a lot, but nothing we couldn't handle. So, right, of course. I always have to start talks with a joke. So here's the joke. The joke is, it's tradition. How many AI researchers does it take to build a robot that can change a light bulb? The answer is, I don't know, but if you invest $2 billion in my startup, you'll find out. One laugh, thank you. So here we go. This is Brett Kagan, my colleague, and Hon-Wen Chong, two of the smartest and most hardworking people I've ever met, so naturally I had to start a company with them. There's also a whole team as well in our company, and just incredible. I used to say it's a 1 in a million team, but some smart-ass VC is like, oh, a million's not that many. So it's a 1 in a billion team. This is really the center of our story. Inside that little ring, right there, I can just point, I don't even need a laser pointer, is where all the action happens. We grow millions of cells in contact with a grid of electrodes. Computer, enhance. So this is a scanning electron microscope image of the dish brain. Here we can see live cells growing on top of a background of electrodes. These are about 17 microns across, and you can see the level of integration here. Computer, enhance. So you can see here in this false color image, we have this electrode grid in the background, and we are processing real-time data from thousands of these electrodes. And in fact, with the right setups, we can even track an action potential moving along a neural procession, which is really very, very cool. But most of what we do is spike detection. So finally, enhance. I just love this particular image because you can really see the level of integration between the cells and the microelectrode array here, the substrate. And you know, in terms of mental model, how are we different or related to something like Neuralink? Well, in the case of Neuralink, it's a brain-computer interface. You have an existing organism, you put the interface inside it. In the case of our work, it's a SBI, or synthetic biological intelligence. We grow the neurons inside the interface. We have complete control, complete reproducibility, and very, very high bandwidth. As you can see, the level of integration is very high. So our basic setup, how do we actually teach this thing to play Pong? 3 steps, easy steps. 1, you got to keep the neurons alive. Easy. It's not easy. Step 2, you got to get information in and out. So that's easy too. And then step 3 is you have to shape behavior. That's where the magic is. So we divide up this neural culture monolayer into a sensory area and 2 motor regions, and then we connect it to the game of Pong. Neuralink monkey plays Pong, DeepMind did Pong, we got to do Pong, right? So activity here is created by electrical stimulation, and it corresponds to where the ball is in the world. It can sense where the ball is. Activity in the motor regions changes where the paddle is going. So it really is a tiny little organism with feedback loop, a constant feedback loop. Some people call this closed loop stimulation because it's constantly interacting with an environment. It's embodied. So here's a little bit more of step 3. How do we actually make these things do something we want? We're putting information in, we're getting information out, but how do we actually get them to do something we want? And we use something called the free energy principle. That's a jargon term, but I'll give you the 30-second version. Neural systems are inherently predictive. They don't like unexpected stimulation. So we, in essence, punish or shape behavior by using a random sequence when it does something we don't want, like miss the ball, and we use a structured sequence that's always predictable to reinforce situations we do want to happen. For example, the ball bouncing off the bat. And with these 2 basic things, a positive feedback and a negative feedback, we can shape behavior. And what's very important here is we didn't tell it like unlike an algorithm, we didn't build it to say, when this happens, do this. It did self-organize to interact with its experience stream to behave. So here is a video of, this is a visualization of our system. I won't talk too much over it, but the point is you've got electrodes in the background, and shortly you'll see activity visualized as the height of the bars in 3 dimensions. This is actually interactive, but I only have a clicker. So each of those blue electrodes is an electrode that we're analyzing real time simultaneously. So the feedback loop is sub-millisecond. It really plays Pong. Okay, next. Hey, thank you. I got a clap for that. That's amazing. And here's a zoomed in one, which is just the game itself. But this is a human neurons or human cortical cells that come from an iPSC line. And this is a cherry-picked example, but what I think is just fascinating about this is that it does tend to anticipate where the ball is going. It's not just randomly following it. And we have a lot of analysis on that. You can read our paper. It's all peer-reviewed. So it just came out in Neuron, the journal. So moving on. This is the first transistor. I just love this picture because whenever I worry about progress we're making, I'm like, you have to start somewhere. So I get a lot of confidence from this picture. I had to put it in. Everything I talked about is stuff we have done. This isn't theoretical. We've done it in our lab. We've published peer-reviewed papers on it. I really, if you get me in the hallway track, I'll talk your ear off about it. What are we doing next? Open dish brain. We're going to allow you, researchers, scientists, entrepreneurs to access neurons in the lab. It's wetware as a service. If you want to talk more about it, please find me afterwards. We're doing drug discovery. We have preliminary data, and I will say preliminary, but essentially we have a collaboration where we have neurons that have a sort of epilepsy. They're a model of epilepsy, and they don't learn until we introduce anti-epileptic drugs. Then they do learn to play Pong. So this has the ability to test not just the effect of drugs on bulk firing, but on cognition itself. Metaverse life. You've got to put this in here. This is what we want. Zuck, if you're seeing this, come on, hook us up. We want to put one of these things native in the metaverse. You want to have a little dish and create the first metaverse native life. And of course, at the start, it would just be for people to see, to be inspired. But hey, that's where things start. And finally, this is the perfusion circuit. It's just so cyberpunk. But this is essentially a system to keep cells alive outside of our lab, because we realize that we can't just be babysitting the cells all the time. So you can see the chip in there surrounded by cool tubes. And this is not stuff we're working on currently. This is more my own personal musings. But in essence, a computer has logic, data, and programs, but they're all separable. You can update a database, you can back it up, whatever it is. They're not integrated. Whereas knowledge inside a neural network is fully embodied within the substrate. The entire sort of nature of the information is integrated into the substrate itself. And learning takes place by atomic level changes within the object itself. This is not what happens in a computer. You can run the same program a million times, even the same neural network on a GPU a million times. The chip never changes. So in a learning system that's embodied, computation, cognition is inseparable from learning. And I think this is really where the future is going to be. Objects themselves, which contain knowledge, which are inseparable from the thing itself. So, of course, I think we're trying to move forward in embodied computing. That means taking something, that means synthetic biological intelligence, that means putting something in contact with the environment, shaping its behavior. And of course, this is the spinal frontier. Okay, like 2 laughs at the front. Well, thank you.